Okay, welcome everybody. Is it possible to slice your startup time into half already today? And will it be possible to slice it even further in the future? I'm Per, I'm working in the core library team at Oracle. And obviously I'm going to talk about the project Leyden today. But there is a lot of other things going on within the Java community. We are running Project Amber, which has been going on for a long time. So far, we delivered 23 JEPs with things like pattern matching and records. We have Project Babylon, which is quite new effort. We want to extend Java's reach to other kind of domains like SQL and machine learning. So Babylon is about code reflection, and that will allow us to reach into the inner parts of your Java code. For example, you will be able to inspect a method and see what's going on inside that and maybe convert it to a kernel that you can deploy on a GPU, for example. We have Project Leyden, and I'm not going to spoil the talk already on slide 1, so let's skip to the next one. Project Lilliput, where we have the objective to reduce the object headers from 124 to 64 bits in the first step, and then maybe even further. That might not sound a lot. Well, that's just 64 bits, but considering you might have millions of objects, that can really make a difference in terms of memory footprint, but also in terms of locality in your code, because now everything is more dense, and then your caches, CPU caches and all that stuff will work much more efficiently. We have Project Loom, which was delivered in 21, and there are still some follow-up JEPs to come, where you can have library threads, like virtual threads, which means now you can use a different program paradigm for massively parallel efforts. You no longer have to use asynchronous constructs. You can use regular threads, which is great if you have exceptions or want to debug. We have Project Panama, which I worked in that project, and we delivered in 22. And with Panama, you can call native functions directly for Java instead of using, JNI and other, trampoline-like network frameworks. That's the word. And also, you can use with memory in a more structured way. So you can have like a memory segment, and you can have structures or unions and things like that. We will see also vector support, but that depends on Project Valhalla, which starting to sound like peace on earth, something we all want, but we will never see. But fingers crossed, I think we will see some deliveries from Project Valhalla real soon now. We also had ZGC, which Stefan talked about in this very room yesterday, which is a low latency scalable garbage collector. And we recently introduced like a tiered generation in that to further improve performance. This is another way of putting it in kind of high speed order. Leyden is looming down the surface here, and it's kind of obscure. And I hope today it will become a little bit more clear what is actually going on here in Project Leyden. Everything we do in Leyden is done in the open. So there is a project page where we have articles and define the objectives of the project. And every code and all code is available on GitHub. So you can go there and see what's going on and keep up to date. Okay, so Project Leyden is about improving startup, warm-up, and footprint of Java application. And now we can do a hand raise. How many of you are concerned about the startup time in Java? Okay, you came to the right place. So startup time is the time it takes to get the first useful unit of work. That is, for example, from when you hit return until you get hello world or something like that. Or if you have a web server, the first request you can serve in your web server. Warm up, on the other hand, is the time it takes for the application to reach peak performance. That is like in the beginning we start, and then it gradually becomes faster and faster. In respect to a compilation that's being done by the JVM successively. Footprint is the third. I'm not going to talk about that so much today, but it is the amount of resources we are having to use, like storage on secondary storage disks and things like that, but also RSS memory. And all of these, they include work done by the application, like parsing configuration files, and also work done on behalf of the application, like loading classes and compiling classes. And all these things are done because Java is highly dynamic. But wait, when I posted this, I had this presentation first earlier this year in Stockholm, and I immediately got this post. Azul VM Graal native image, in my opinion, it is a solved problem. And that might be the case if you are willing to give up or concede a lot of dynamism in Java. So for example, if you compile to native code, you won't be able to load classes dynamically. You won't be able to use dynamic proxies, for example, unless you have specified them in advance. And there are also a lot of other things you can't do. You can't do certain types of reflection. And I think the big thing is that you can't even rely on a library that does this itself or transitively relies on any of these features. So that will kind of restrict you severely. And that might be okay in some cases, but in most cases, it's not okay. Then some hours later, I got this tweet here. Sample Spring Boot, app time to first transaction 4 seconds. But if you use product crack snapshot, for time to first transaction is 40 milliseconds. And that's 2 orders of magnitude faster. So doesn't that solve the problem? Well, that brought me to think about this thing here. So when I started to code, I was like 13 years. And after some years, I got this Commodore 64. And we were kind of a team of youngsters who liked to play games, who liked to code games. But we didn't have a budget. So, of course, we tried to crack the games. And in fact, it was legal in Sweden at that time to do that and even share it with your friends. And we got pretty good at it. But, you know, there was this constant arms race. And so eventually this came out. And this is something called the ice pick. So what you did was that you put it into the expansion port. You reloaded a bootstrap code, which went into this 8 kilobyte RAM socket, the big one there. And then you flip the switch, and then you load your game. And then you flip the switch again, and that created a non-maskable interrupt, which jumped to this bootstrap code there. And the bootstrap code will create a copy of the disk of the entire memory, you know, all the registers in the graphics interface, sound interface, timers, and all that stuff. So this effectively created a snapshot. And this is very similar to crack, which does the exact thing, but via software. So the switch there is just a command. Like this one only works for the Commodore 64, crack only works for Linux. And that might be good enough, but the problem was the same with this one, because there was yet another arm race. Well, game developers, they put, you know, values and secret stuff into things that were not touched by this item. For example, putting obscure dividers in some timer registers and things like that. And then it was able to detect that this guy was actually being used. And it's the same thing with cracks. So you might have stateful information. For example, you might have file handles in your code. And when you restore the image, those file handles are no longer valid. Or you might have a cache while you have timers. And when you restore it a week later, those timestamps are not really relevant. So what you have to do then in order for this to work is that you have to register all these entities that keep track of file handles or custom caches or whatever is affected by the snapshot. They have to register to a context, and they have like 2 methods. One that's being invoked when you save and one that's being invoked when you restore again. So that's a big change to the program model. So that means that it's kind of not acceptable if we want to use Java the way we are used to. We want to be able to use Java on all platforms, for all programs, and preserve program meaning. So that's the objective of Leyden. We want to shift computation temporarily, later or earlier in time. We want to introduce constraints on Java's natural dynamism to enable more and better shifting. We want to do this selectively per needs of each particular program. So we want the programmer to be in charge. What do I want to concede? And lastly but not least, we want to do this compatibly, preserving program meaning, which wasn't the case in the 2 previous examples. So I'd like to think about this as a mixer board. I like to play music, and you have different instruments, and for some instruments you have low value, for some and others you have higher volume. And it's the same here. You have knobs. You can, you know, enter concessions you want to make. Maybe for some programs you don't want to make any concession at all, and then maybe Leyden can give you a little bit of better performance. And for some others you can concede a lot, and then you get better performance. but it's all up to you as a coder. Okay, I've already said that Java is dynamic several times, but wait, isn't Java a static language? If we mean by static, we mean at compile time. So is Java static or is it dynamically typed? And the answer to that is yes, it is. It has a static type system enforced at compile time, but it also has a dynamic type system enforced at runtime, because some of the things aren't possible to determine at compile time. For example, entering stuff into an array that must be checked on runtime. So we have this kind of both worlds here. So some things are actually static. We have generics, checked exception, definite assignment analysis, overload resolution, and so on. We can do that compile time, but other ones are dynamic, like array store exceptions for array writes, for example. So Java is both static and dynamically typed. And when we have this kind of contradiction in terms, it's often useful to go to a dictionary and say, what do we mean by static and dynamic? And I think static is like at rest, not moving so much, remaining at the same place, not changing. Whereas dynamic is energetic, moving around and changing. So I think it's better to talk about changing versus not changing. And one aspect of that is what is changing. And in context of languages, we often think about static versus dynamic type checking. But Java has so much more dynamic things. We have dynamic typing, like I spoke about before, array store checks. We have dynamic class loading and verification, dynamic class redefinition, dynamic compilation, like when we launched the JIT compiling. We have dynamic recompilation, which we call de-optimization. That is when we have made a compilation for some statistic or for some precondition, and when that statistic changes or the precondition fails, we just de-optimize and go back again, and then we can do a new compilation a little bit later. We have dynamic linkage and access control. Every time we call from a call site, call a method, we need to ensure that we are actually allowed to do that call. And of course, we cache this information, so we will still have good performance, but the first time we need to do a little bit more work. We have dynamic dispatch, which is if you have an interface, then you might have several implementation of that. So that's called virtual methods. We have also dynamic introspection, like instance of and reflection. So if we look at all this, I think we can conclude that Java is pretty dynamic. Another important aspect is over what period is something changing or not. So we often think about compile time and runtime, but in reality they are kind of blurry. So we have, for example, this statement here, static fileman long app start microsecond equals some timer up there. So is this static or dynamic? Well, it says static on the tin, so in some sense it's static. But the initializer runs at runtime, so that's kind of dynamic. But the variable here is held for the constant time of the class loader or when the JVM exits. So that's a bit static. But then again, the lifetime doesn't coincide with compile and runtime. It's another life cycle. And I think the JVM is good at this. I mean, it can see that, well, now this is really set, this variable, so it can assume it will never change anything, more in the future. So it's kind of born dynamic, but treated as a constant. And we have this kind of yin and yang between static and dynamic. Apologize for the old picture there. But the JVM deals with this routinely. We have static field initialization, we have class loading, we have many JIT optimizations that relies on this fact. For example, we have this class hierarchy analysis, speculative optimization. Let's say you have a sealed interface or you have an interface that is not sealed. And then the JVM knows that there is only one implementation of this interface. Then, of course, you know that any method invoked on the interface is going to be mapped to exactly the invocation of exactly that implementation. But then, after a while, you might load another class, and then the same JVM as that has done the compilation can see that, oh, I assume that we only have one implementation, but that invariant doesn't hold anymore. Okay. So I can go there and evict the code cache and say that you cannot use this optimization again, and then we can just wait and get optimized again a little bit later. So this is something called profile-driven de-optimization, which is similar, not the same, but the profile-driven de-optimization is when the characteristics of your data changes, and then you might want to do something else. Okay, what happened at startup? So things that are dependent on your program and the libraries you're using is like reading configuration fields, you are scanning for annotation, opening sockets, registering listeners, and creating loggers. That's very typical if you have at least a web application. And when you do this, the JVM will act on behalf of you and load classes, reading from disk, validate the class files, constructing metadata, and run static initializers. And when it starts, it will run in interpretation mode, and it will gather profiling, and then eventually it will compile. And we have also this call set linkage and constant pool resolution, which I just talked about. Okay, so that's that. What happens during warm-up? Well, we might populate our own caches, like we want to read things from disk and store them somewhere, so we don't have to read them from disk upon every invocation. And the JVM will act on that and will compile code. I will come back to exactly how the compiler works. So why do we do it in this way? Isn't it silly to go through all these processes all the time? Well, not really, because it makes Java so much more expressive, gives us so much more power. So I really think this is a price worth paying. And the thing is that if we use dynamic compilation, we might, under some circumstances, actually get better performance than if we compile, for example, a C program. Now, you shouldn't construe this that I'm saying that a Java program is always faster than C. That's not the case. But in some cases, it is, because we know exactly the current hardware configuration we are running on, even the stepping of the hardware. We know the profile data that actually runs on this program. And we can optimize according to that observed behavior, not only the code. So that is great. Yeah. And that is something we pay for. And for some cases, it's not good, but in many cases, it's a good trade-off. Consider, for example, a risk analysis tool that wasn't even updated since the Lehman Brothers crash. And that is something that you can just keep on running. It never changes, so it will, be warmed up and stay there for years to come. So let's look at this in a more, academic point of view. Let's say we have the green bottom line here, which represents some kind of ideal solution. So the first request will take a little bit longer because we might populate our caches, might read configuration from files and so on. But then the second and the third will go much faster because we have already cached all the information we needed. But the typical behavior of Java is something more like the yellow line. It will take much longer time the first time we run, and then we will have this deficiency against the ideal case that will kind of decrease over time, and eventually we will read the idle kind of level for response time. So we have this class initialization activity that is unique to the first run, and then we have this kind of warm-up deficiency under here, and it's really the things we are losing here is really the integral between the two curves. So what we need to do is to try to improve startup to push down the first point, and to improve warm-up, we need to push down the entire curve down. And how can we do this? Well, in order to do this, we think it's necessary to shift work of the critical path. So we can shift work later in time, such as by laziness, and we can shift work earlier in time from runtime to build time, or even maybe introduce a new build pipeline that can do stuff and transform our code. And we already have a lot of techniques that does this today. So we have constant folding, for example, that shifts things earlier. So the compiler can see that this is never going to change, and this is a constant, which in turn contains a constant, and it can fold all that constant and just store that value. We have garbage collection, which is actually something we do later. We say that now we don't need this object anymore, but the JVM is free to do this collection of the garbage at any time later. So that's something that is lazy. We have lazy class loading and initialization, which postpones things to a later time. So we don't have to initialize all the stuff when we start up. Some of these things requires an action from the user, for example, in using AOT, ahead of time compilation. and using the CDS, which I will come back to later in the presentation. But shifting is, fair game as long as we preserve program meaning. If we go a little bit further down, we can see that the Java memory model is quite sophisticated. We might want to think that if you run something in mutate memory, other thread will see that just like the mutating thread, but that's not really the case, because the memory model only guarantees that within a single thread, it is as if serial semantics that is upheld. So if you have, for example, A equals 1, B equals 2, and then C equals A plus 1, for example, then it's not necessarily done in that order, because you might want to shift the initialization of A and B because you already have A, and then you want to have A when you construct C. And that is fair game too, because it preserves the meaning within the thread. But if you observe the modification from another thread, the other thread will see that this will happen in a different order. And that means that we have something that calls happens before. And happens before can only be assured across threads using some kind of barrier, memory barrier. So that is one thing that can shift and change the way we compute things. And if we go even further down into the hardware, we have out of order execution. We have speculative branching. We can do several operations with SIMD. We have CPU caches, for example. Let's say we update the value to memory, and the hardware might say that, oh, we will just write it in the cache, and then later we might update it before it's written back to main memory. And that's also a way of doing things lazy. So there is this shifting going on all the times on different layers. So this is not something new. It's just that we add another layer of moving stuff around. And Leyden will expand all these shifting opportunities. So one easy thing we can do to expand lambdas into ordinary bytecode at build time. And that will shift things earlier. You might know that if you have a lambda, the lambda always implements an interface. And therefore, we will create a new class that implements that interface under the hood. There is a certain feature within Java that provides that for us. We can, for example, speculatively compiling code ahead of time. That's fair game too, because we can always provide a compilation, and then if the invariant doesn't hold for how that was compiled, we can just throw it away, evict it from the code cache, and start all over again. And we are also considering some new features here. We have talked about maybe adding a keyword called lazy. At the second lowest level, you can see lazy static final foo, and then we have some kind of lambda there. So when we first reference foo, the lambda will be computed. Another thing we are working with is something called stable value. This was originally a part of Leyden, but now it's kind of a free agent. It's running in a separate, and it's actually yours truly. I was driving this together with Maurizio, and it has a separate JEP. And it's kind of cool because now you can expose an internal thing that is in the JDK called stable. Stable is something that the JDK can see, and when it has a stable annotation, if the value has changed from the default value, then the JVM knows that this is the final value. It will never change. And that is true also for like ints and shorts and all that stuff. So an int's default value is, of course, 0. So if we can observe a value that is not 0, we know that this is the value. It's never going to change. But the stable annotation is not safe for ordinary users, because what happens if you change this? The compiler might have done presumptions that it will never change. And if you change it anyway, well, your program will break. So what stable value does is that it provides a safe wrapper around the stable. So if you have, for example, you can say that you have a stable value, a logger, and then the stable value off creates a fresh instance of a stable value that is unset. And then later on we can say compute if unset, and then we compute our logger here. So it's very similar to the example with lazy keyword and so on. This is more of a library approach. And the good thing now is that stable value will be as fast as if you were to declare it as just private static final logger. The JVM will see through the stable value wrapper, and it will constant fold this value to whatever we set here, but we can set it later. So this is a way to kind of decouple final to its initialization. Normally final has to be set before the constructor ends or before the class is initialized. But now we can set it much later, actually whenever we want, but still gain the same performance as a final field. So this is the kind of best of both worlds. Yeah. So this is basically what I said. And it provides benefit. The previous example was in static context, but it also is better for instance variables. So you can use something called a class holder idiom, when you have a class that holds a value, and you can have an inner class that holds a value to delay computation. But of course, that comes with a price. You must add static footprint by defining a class that you're actually not really using. You're only using it as a wrapper. But you can also use something called a double check locking idiom if you have an instance variable. Of course, you cannot use a static class to hold an instance variable. And it's a replacement for both of this. So now here is an example of using, in a static context, stable value compared to using double check locking. And you can see in all platforms, this will give us a significant performance improvement. I think that's great. Not only will your code run faster, but will consume less energy too. And it's not only restricted to a single set of a value, it's just the concept is expandable to list the maps. So in this example, I say I have a map of something that goes from a string to a stable value that holds a logger. And I have these two allowed keys, which is com_foo bar and com_foo baz, that I can use in my stable map. And then I can just say that I want to compute my logger using any name by invoking this getLogger method here. And then this map will be as fast as an immutable map, creatable map.off. So actually the JVM is able to see through all this map and all the way to the constant value and can constant fold the operation here. So this is a more interesting example. I think we all have seen this in computer science. We have the Fibonacci series. And this relates to something called memoization, which is related to caching. So I say that I have a Fibonacci interface, and that has a method that can compute the Fibonacci value for values from 0 up to n. And of course, it's the sequence 1, 1, 2, 3, 5, 8, and so on. So a very naive implementation of this problem would be to use a recursive solution. When I said when it's less than 2, it's n, and otherwise I will recursively invoke this method for n-1 and n-2. And this will kind of build up the structure on the stack. And every time we call this method, we will have to create everything anew. So what we can do then is to use, and this is of course very slow because it can be shown that the problem will grow exponentially. So if you invoke this with Fibonacci for 1 million, for example, it won't complete. So what we can do instead is to use the memoized function. And then we say we have an int function because the Fibonacci function is an int function. It takes an int and it returns something, which in this case happens to be an integer. And so we use a stable value of int, and we say that we have this many slots that we want to cache into this memoized function. And every time, for the first time we call something for a slot, like 5 or 7, we invoke this method here called this fib, which actually computes the value, just like before. And the cool thing here is that we are recursively using our memoized function. So the memoized function refers to itself. And actually, the stable value is clever enough to figure out this and still be able to constant fold values here. So this is a very powerful way of building up effective programs. Okay, back to the main program. So constraining dynamism. How can you constrain dynamism? Maybe you can say that class X won't change, or maybe you can say that no class will change at all, and I don't want to use reflective operations like in the closed world example I had before. Or maybe it's more fine granular, that no class definition for module M. So the exact set of this limitation is not really set in stone yet. We are still experimenting with these. And the reason, and that brings us to the next step, because we are talking about introducing something called condensers, and I think that is the name why it's called Leyden, because Leyden was an old condenser. And a condenser is something that performs a computation on a representation of a program image by shifting things earlier in time. So it can be like we can add new code by compiling code. We can add new data, we can add new metadata, and we can also add new constraints, that one constraint imposes another constraint. And the good thing with condensers, let's see here. Okay, something wrong here. Okay, there we are. So condensers are meaning preserving. So the result from when you apply a condenser means the same thing, but might have another representation. And condensers are composable. So if you have condenser 1, you can apply then condenser 2 and condenser 3 and so on. And you can even go back again, like an optimization in C. You can do several rounds of optimizations here. And condensers are selectable. Maybe if you are running debug session, you don't want to run any condenser at all because you don't care. And you want to view the code as true as possible to the source code you have. But maybe in other cases, before you deploy to production, you want to invoke several condensers. Okay, so I will talk about CDS and class data sharing. How many of you have used app CDS? One person, one person. Okay, in Stockholm there were 2 persons, so it's almost as good, but it's not. This is a very unknown thing, and I saw a lot of more hands were raised in the beginning of the session here. So I will come back to what you can do, and you can actually use this today. So app CDS was added very early. Yeah. So it means that for the first time you run the JDK, it will do a lot of class initialization of internal JDK classes, and it will then store a representation of those in a file. And when you start up, you don't have to go through all this process of doing all the class loading and all that stuff. You can instead go to the file and just load them. And it evolved over time. So in JDK 8, we can dynamically generate Lambda proxy classes to save time. And then in, I think it was 10, we have app CDS, which unlocks the CDS for application data as well. And that is key to improving startup time within Leyden. Okay, let's skip this. So here is how you can use it. So you can have a XX flag that you want to dump the loaded classes on a file, and you can run your code several times. So you can just merge those files, and then you run this command again, and then it will take all your classes that are in this file, you can edit it, and then it will create this app CDS that will also, apart from the JDK classes, contain your classes. And then when you start with the other flag here, it will kind of boot from this CDS archive directly. And here is an example. If you had explicitly disabled CDS, it took like 300 milliseconds. The default setting with all the JDK loaded, about 250. And with app CDS, what was 150. So now I think I can answer the first question I asked in the beginning. Can you slice your startup time into half? And I think the answer is almost yes here, at least in this example here. So if you are concerned with startup time, this is something you can do. If you just search on the internet, you will get a lot of articles about this. And I think app CDS will be kind of packaged as a condenser because this is kind of tedious work to do. So that should be a more, nicer way to do this. And the app CDS, as we are also going to see, Leyden relays on something called a training run. So you typically run your application during in some environment, and then you harvest information from that training runs. And it usually requires writing a small driver program, like an integration test. And I think it's good that also the integration test will run on data that you regard as typical to your application, because that will affect statistics gathered for your code, and that will give you a better startup performance. Okay, so let's look at some figures. How far can we get using the existing hotspot components? Before I go into the details, I just want to mention the circle of life for Java code. So when we start, your application is interpreted. And then when we do that, we gather full kind of statistics or profiling of how your codes are being used. For example, what are the percentage of branch taken from this if statement and so on. And then eventually we advanced up to tier 4, which is a C2 and Graal compiled, when we don't do any profiling anymore. We just use the profiling we have. And if we hit the wall and it turns out the preconditions we had for generating this code and putting it into the code cache doesn't hold, well, then we need to de-optimize, and then we are back again to square one. And this is something that's going on all the time. And you can actually set some flag and see what's going on when things are traversing this graph, and you get that on the output logger. Okay. So this is kind of something called speculative compilation, and we can always fall back. So that is the idea with Leyden. So we just run this test run, and we do compile things, and if it fails, we just throw it away. But usually it won't fail because it will hopefully be similar to the test code we did in the try run. Okay, so the next step in Leyden is to teach CDS new tricks. Today we can't put this stuff into the code, into the CDS. The data format doesn't allow that. But there is an idea to be able to store profile gathering, compile method, class objects, resolve constant pool references to classes and method and fields, invoke dynamic linkage status, and pre-initialization of enum and hidden classes, plus a little bit more. And that will allow us to run things much faster. In fact, reading a CDS++ file is about 100 times faster than just computed it every time. Okay, so let's skip this well. So here I have some case studies. So this is a very simple test. We compile 100 small Java source files. And the baseline is the yellow line, and the green is some kind of imagined ideal case. And the red one is the Leyden. So in this case, we have run it before. We have gathered all the information, compiled code, put it in the CDS++, and off we went. And that gave us actually 2 times startup improvement for this. And I think that is very encouraging. Not only did we get better startup, but we also got a warm-up improvement. So that is very promising. Okay, we didn't do any concessions here. We just used the code as it was. So no special tricks, no sliding on the mixer board. And here is another case study we did. This is like parsing an XML file. And here we got an even better startup. We got 8 times better startup performance. But the warm-up performance wasn't that big. And I think this has to do with the workload. So maybe this was more about starting up and doing something and then not doing the same code path so much from time to time. So it really depends on what kind of application you have. Okay, so here is another benchmark using Spring Boot. There's something called Pet Clinic, which is a kind of hello world for Spring. It's not just printing hello world, but it does. It's kind of a real web server, but it's very limited functionality. And the red one is the baseline JDK22, and then we did some tricks: static CDS, unpacked, and with dynamic CDS, which is the Leyden stuff. And it says here it's 4 times 1 faster, but I think it's a bit unfair because, I mean, who is not using CDS from the beginning? And there were also some other tricks here, but it gave some improvement at least. So what really was paying off? Okay, there was a lot of improvement, but they all work together. So we have early class loading, was really a big win. Caching compile code, big win. Resolving invoke dynamic calls, well, it was a win, but didn't help out the situation so much. Same with tier 4 coding. I didn't talk about this, but because this is a bit complicated, but you can do kind of speculative compilation under certain assumption, and then you can change your assumptions as you go along. And Springboat's ahead of time configuration tool is a big win. You might know that Spring has its own optimization to reduce startup time, and that's good. And I think we can potentially in the future see the Spring optimization at yet another condenser. So it's possible to generalize Spring's kind of optimizations via a condenser. Here are some more recent figures that were recently put up on the project. So here we have a Helidon quick start. The mainline default is normalized to 1000. And then we have a custom static CDS. And then we have the pre-main. The project within Leyden is called pre-main because we are running things before we run the main class. So we run the main, harvesting compilation and statistics, putting it in the CDS. And then we have pre-main together with ahead of time compilation. And that is about 3 times or even more than 3 times faster. I think this is the more representative image of what we can expect. We did this for a number of frameworks. So here's for Micronaut, pretty much the same. We have Quarkus, also very similar. And then we have Spring Pet Clinic, more recent figures. And if I kind of play this like a film, you can see that they pretty much stay the same. It's a little bit variation, but the big, outline remains the same. So we will have about 3 times better startup. And if you're interested in exactly how these benchmarks were made, on what hardware platform, how the program looks like, you can go to this link and check it out. I'll leave it there for a second or two so you can take a photo. Okay, so time-shifting speculative optimization works. It's a very promising concept. Significant gains, full compatibility, no new constraints, no changes to the programming model, no changes of specification, and it retains all Java's natural dynamics. And the next step is kind of to introduce this selective way of conceding to dynamism and introduce additional things that can make it even better. But first up is to create something that's called CDS++ informally. And we already have a JEP for that. And you can find that at that address or search for list of JEP. And then you will find this one there. When we will see this, it's not decided yet, but I think pretty soon. So next step, introduce condensers. Involve the Java platform specification to support condensation. We want to accommodate new metadata. We want to, explore more ways of restraining dynamism in a good way. And we're just getting started. It's early days here. But the first drop of Leyden will be this kind of CDS++. And maybe we're going to see stable values soon. So that was what I have to say today. And with that, I open up for questions. Thank you. Any questions? Okay, yeah, I was blinded. Okay.
You say de-optimization.
Yes.
So correct me if I'm wrong. My understanding was you would only revert back to interpreted and recompile if something is found that where the previously compiled version has broken the semantics of the program. So something like you thought an interface only had one implementation and then another one was found and it has to recompile for that reason. Is that true, or are there cases where you would de-optimize just because it thinks it can do a better version of the...
I rephrase the question. So the question is, what about the optimization? When is that triggered, more or less? And it can be triggered in many kind of triggers. So one trigger is that you have assumed something and that doesn't hold anymore. For example, maybe you invoke your method with something that is never null. And suddenly it is null. And then you generate a trap and say that, wow, this failed, it blew up. Because I can do optimization assuming it's not null. And that's one thing. And another thing is that when you run your data and suddenly you have another statistics, you might see that, well, it might be better to go back and de-optimize again.
So that happens as well then?
Yeah.
That's separate.
Okay, another question? Yes?
Can the CDS information be packaged with the actual applications? Multiple runs, they have to be on the same environment.
Yeah, so the question is, can you package the CDS and does it change? And the answer is that you need to have the CDS++ file on the exact same layout that you are running it on from the beginning. So you can't take the CDS file and put it into another platform, for example, because the compile code won't work. It might be another CPU or another architecture. So you need to keep that in mind. But you can, if you have the same platform, you can put your file wherever you want, and you can say that my CDS is here. You can check it in, or you can have it in your package it in a jar file or whatever.
Scenarios like you can also when you deploy multiple pods of your application, use one to run this and gather all the information. The other pods for the other pods to start up quicker without having to do multiple runs. You see what I mean?
I can't hear you. Sorry. Yeah.
I'm thinking about an example when in OCP, for example, when you have multiple versions of multiple instances of your application running, you can use one of those to do the CDS data, gather that, and then share it with the other.
Yeah. Okay. So the question is, can I run this for once and then can I deploy to hundreds of servers using the same platform? And the answer is yes, you can do that. So as long as it is fairly equal, you can just do one training run, and then you can ship that to your, maybe you have a cloud application and you have 100 instances, and then you can run it on all 100 instances, which are standardized.
Basically, they will get the advantage of the first time they start, they will be quicker.
They all will boot from the CDS and start quickly. Yes. Okay, anything more? Okay, guys, thanks for having me today.